In this video, I present the rationale for introducing chemical potential. We have learned pressure, volume, temperature, and entropy. We have also learned internal energy, enthalpy, Helmholtz energy, and Gibbs energy. We learned how these thermodynamic functions depend on each other. But now, why do we need another thermodynamic function, chemical potential? Well, I'll use several examples, from the simplest to the more complex scenarios, to justify the introduction of chemical potential. Now later we will see chemical potential connects U, H, A, and G. Chemical potential is the central piece of thermodynamics. Now let's look at a very simple system that consists of a single species with a fixed amount, and this species is in a single phase. And then the Gibbs energy of this system is a function of only two independent variables. We can pick any two from P, V, T, S, but for convenience, we write dG is equal to negative S dt plus VdP. Negative entropy is how G depends on temperature. Volume is how G depends on pressure. Now let's make it more complicated. What if the amount of this single species may change? And then we have three independent variables. Other than temperature and pressure, we have the amount of this species. And now Gibbs energy is a function of T, P, and N1. dG can be expressed as delta G over delta T times dt plus delta G over delta P times dP plus delta G over delta N1 times dN1. And we need to pay attention to the subscripts over here. Temperature and pressure are held constant. So what if temperature and pressure are indeed constant? Then dt is 0. dP is also 0. dG is simply this term, delta G over delta N1 times dN1. Now, what's delta G over delta N1? Well, it's simply molar Gibbs energy of this species under the specified temperature and pressure condition. More generally, you can say it's the partial molar Gibbs energy. And then, what if we make the system even more complicated with two species, or a single species in two phases, for example, water in the gas and liquid phases, and then we need to introduce one more variable. We have N2. Alright, either we have two species or one species in two phases. Now we have four independent variables: temperature, pressure, N1, N2. And then we put those partial derivatives in front of those exact differentials. And also we need to pay attention to the subscripts. Over here, Tp and N2 are constant. Over here, Tp and N1 are constant. So again, when there are two species or a single species in two phases, they should be treated as two species. In a system, we have four independent variables. Again, G depends on temperature, G depends on pressure, G depends on N1, G depends on N2. Now, what if we hold N1 and N2 constant? Well, in that case, dG is simply delta G over delta T times dt plus delta G over delta P times dP. Over here, again, we have N1, N2 constant. And for this dt term, we hold P constant. For the dP term, we hold temperature constant. And also, we know this: if the amounts of all species in the system are fixed, we have dG is negative S dt plus VdP. Negative entropy is how G depends on temperature, which is just this. And volume is how G depends on pressure, which is just this. And then we get the expression for entropy and volume of the system with two species. Negative entropy is delta G over delta T when pressure N1 and N2 are constant. Volume is delta G over delta P when temperature N1 and N2 are constant. In general, we can write out this form. of dg. dg is negative s dt plus vdp plus the sum of delta g over delta ni dni. So when we evaluate this partial derivative, temperature, pressure, and well, the amount of all other species should be held constant. The last term can be simplified upon the introduction of chemical potential. Later we'll see this part, this partial derivative, is chemical potential.